my browser. No, please. Not now. Really, all a differential equation is, it's an equation that has a derivative in it. That's all it is. There are entire classes about differential equations. They're useful for a lot of real world kinds of things. Yeah, close the window. So there, it's definitely definitely more than a passing kind of a thing, these differential equations. We're going to touch the tip of the iceberg with these. So a differential equation, oh yeah. So I'm going to write what I said, an equation that involves a derivative. The order of the differential equation is the highest order derivative that it contains. So if it just contains a first derivative, it's a first order differential equation. If it contains a second derivative, it's a second order differential equation, and so on. And then there's partial differential equations, which we're not going to look at all, but related. So here's one. It's an equation with a derivative in it. There we go. That's a differential equation. It's an equation, and it involves a derivative. We can solve this, right? How am I going to solve this differential equation? If this is the derivative, how am I going to find the function? Yeah, we're going to do like the opposite, the inverse of a derivative, which is integrate on both sides. It's not really any different in principle than when you were way back in Algebra 1 and you had y equals, or x plus 3 equals 5, and you subtracted 3 from both sides of the equation to find x. Same idea. We're going to integrate with respect to x because that's the variable. On the left, we get y. On the right, gee, this looks familiar. Like something we might have been doing recently. What do we get when we integrate on the right? Most. One more thing. Yeah. Yep. So solution to a differential equation. I get this family of functions that are different by a constant, but yeah, that's it. This particular differential equation we would call an exact differential equation because we have dy dx equals this exactly. There, we don't have any kind of x's and y's mixed together over here. The derivative of y with respect to x is exactly this function in terms of only x, which implies that there are other kinds that are not exact, and there are, but not today. There's only these kind. I'm pretty rapidly going to go to diff eq for differential equation. So I get this family of functions from this exact differential equation with the plus c on the end there, and we know that constant can be anything, because if I take the derivative of this, no matter what the constant is, I'm going to get dy dx that I started with. What if I want a particular solution instead of just the generic family of functions here? Well, if I have an initial value, a particular function value, I can do that. I can narrow down this family of functions to one specific one. So an initial value problem is, we're still talking differential equation here. With a specific point on the solution that's given, so that you would have that at the beginning. You don't have to guess or anything. So when I have a specific point, I can find a specific value for c and one particular function as a solution to the differential equation. It narrows it down from all of them to just one of them. But the words we actually use are particular solution. As opposed to a general solution. For example, here's one. I go with 3 sine x. And y is 2 when x is 0. So that's a point. 0, 2. So I can find my general solution. What's the general solution to this differential equation? You don't necessarily have to write the step where you integrate. I'm probably not going to for exact ones like this. What's our general solution? Am I blurry? Not do anything? It must not have done it. I tried the autofocus thing. Did that not? Oh, better? Okay. Okay, so there's my general solution, but we're not done because I don't just want the general solution. I'm the particular solution, the particular one of this family of functions that has y equals 2 when x is 0, and there's only one that does that. So next thing I'm going to do is go like that so that I have more paper. And then I'm going to fill in y is 2 when x is 0. When I do that, the only thing I don't know is c, which means we can find c explicitly. What's c? Cosine 0 is 1, add 3, which means we're not done yet. Now we got to write the whole thing. The particular solution to this differential equation with the initial value is y equals negative 3 cosine x plus 5. That's the only one that meets that initial condition. Questions so far? Okay. Let's practice a little bit here. We get kind of hung up on x and y. We use x and y all the time, but they're nothing magic about x and y. So I'm branching out. This time I have u as a function of t. So I wrote du dt. I'm just looking at my paper. I will show you because it's funny, I think. There's what I wrote on my paper. What's the problem with that? Yeah. du dt, and then I write x. It's a habit. Boy, those habits get ingrained, right? So I'm going to do it with t's. That is the function we're going to use, but we're going to call them t and not x. And we'll see if I can manage not to write t's for the rest of the time. Oh, yeah. So 7t to the 6th, 4t cubed, minus 5, and u is 1 when t is 1. There's my initial condition. So I'm going to be quiet for a minute. Let you go ahead. See what we get for a particular solution to this exact differential equation. I'm partial to Q myself. Q hardly ever gets used for anything. So when you have a solution, go ahead and put it in there. Let's see if we have a bunch that match. Oh, we do have a bunch that match. Yay, that's good. I'm going to go ahead and do the details here. We get C is 4. And we substitute 1 in, set equal to 1. We get 4, so particular solution. There it is, and that's the only one that both has du dt as its derivative and satisfies u of 1 is 1.